ceiling function, from where does it come? Well, as we are moving from functions, the general functions so far we've been talking about, we are moving from functions to discrete function, right? What change do we see? We see that our continuous lines and continuous graphs where the domain was x belongs to real numbers immediately changes to x belongs to set of natural numbers. Now that's a huge difference, but people think, well, it's not much, just forget about decimals and fractions and all that which was giving us trouble. Now that should be easy and simple, right? But I've found that still it is not simple. It becomes more complicated, really very complicated. Now to solve that complication, I thought I will explain you two new functions, okay? So, the story goes like this. If the problem is complicated, then make it more complicated. Then the previous problem will look simple. So that is what I'm going to adopt here. So I'm going to hit you with two more functions, and that is one I'm called ceiling, right on the top of where you're sitting, and the floor down below, right? So you are in between these two functions now, ceiling and floor, okay? Remember that. And see how we are going to connect that to discrete functions. That is the whole exercise which I'm trying to do in this video, okay? It's a maths video, right? Well, there is less math here, but more of arts. Both are so close to one another that I really can't distinguish between them. Now here it goes. Let's look into both the functions, right? Let's take one function here and a discrete equivalent here. So we have a straight line. Let's say we have a straight line here, right? Now that is kind of a straight line. In real, we are not really bothered. Domain is all real numbers. Well, there you go. Perfect. Now, if I have to draw this straight line equivalent here, then what I do is that I just forget about those parts because my domain is set of natural numbers and I cannot be like on the left side or even on the y-axis. So what I do is I draw like points here and I get like this, that kind of a thing when I want a discrete function angle, right? So those were actually the points which we had in our table, but now we cannot connect them because our set is set of natural numbers and not real. So we can't connect them. We just put the points as they are. Well, that's one part to it. But that's simpler part, right? Now as soon as we enter into discrete functions, we land up into many difficult problems. And there, what happens is, let me give you one more example here. Let's say we have something like this, right? And what happens is, let's say we need to somehow convert this information, and there's also a straight line. Let's say this is a straight line here, right? We need to convert this information somehow into the form of a discrete function. I'll take a concrete example with you. Example here is like, let's say we have school children going for a picnic, right? And let's say there are 1,000 students, right? The whole school is going, for example, and they hire some buses to go. Now the teacher says, well, if the student number of students is A, then the cost will be fixed cost plus the cost per student, right? Now that is the kind of cost they have, and what they really do is they draw a line like that because it's a real, so the function is real. They just draw a line and they get away with it. Now here in discrete function, it is really very complicated. First let me simplify the problem for you, and then we can think about complications, okay? The complication here is, so I'll simplify the problem. We'll say fixed cost only. We'll forget about the variable cost for the time being, okay? Fixed cost is, let us say there are 1,000 students in a school. They want to go for a picnic, and they can hire a bus in which 60 students can come, right? And a bus will cost them, let us say $200. Okay, fine. If bus costs them $200, then as soon as one student, when there is zero student, you don't really pay, right? You don't pay, right? So at zero, there's nothing, and it's good for us because it belongs to natural numbers, and n is not really zero. So n, you need to have someone there to pay for it, right? So if first student comes, then you need one bus, and since you need a bus, you have to pay for it. So that means pay $200, right? So let's pay $200 here, right? That is the dollars here, and here we have number of students. Let's say n, the number of students. Okay. Now the second, third, fourth, all can get into this bus, right? And let's say the capacity is 60, right? We say capacity of the bus is 60. 60 of bus, right? So up to 60 students, they can come here. So let's say this is 60, right? In that case, fine, we fill this up. Okay. Now what happened? If 61st student comes, then we need another bus. So we need another bus, right? 61st student. So we can start with 60, saying, well, 60 will pay $200. But as soon as the 61st student comes, then we need another bus. And that's why we got to pay now $400. Correct? So we pay $400, and up this can accommodate 120 students, right? Well, after that, we can go on and on. Well, not much. We have got 1,000 students. So there's some respite. Anyway, what we see is these kinds of lines coming up, right? And for every 60 students, additional 60 students, we need additional school buses, right? And now we can pay 200, 400, 600, and so on. Correct? Now here's huge difficulty. To represent this as a function, where we're trying to say, well, if the number is between 0 and 60, then it comes into one bus, and as soon as it becomes over 60, we need a new bus. So additional bus, correct? So that is how it becomes. And if you really try to make a general equation for this, it becomes too complicated. We are trying to understand a couple of things here. That means we have cost, right? Which is related to buses, right? Which is related to number of students, right? Number of students. So it's function of function. It's no more such a simple function, right? Otherwise it was so simple for us, right? Now here, how to do this kind of problem. So I'm introducing ceiling function for you so that similar problems can be taken care of. Why I chose ceiling? See here. If I divide any number, let us say if a number is less than 60, let us say it is 30, right? If I divide 30 by 60, what do I get? So I get 0.5, 0 point something, right? Now, ceiling means you can round it to the higher natural number. So 0.5 higher will be 1. So you need one bus. Do you understand? Even if I do 59 over 60, right? What will I get? I will get something, but less than 1, right? It will be 0. I don't know exactly. We can always use a calculator, right? And say, well, what is 59 divided by 60 equals to? 59 divided by 60 is equals to 0.98, so on. And 3 recurring. But it is less than 1. So what we do is, but we know we need one bus, right? So we again round it to higher. That means going towards the ceiling on the top, right? Do you understand? Even if I have 1 over 60, right? 1 over 60 will be 0. What? Let me calculate and let you know this also. 1 over 60 is 0.01. Oh my God, so small number. 66 recurring. But still, it is point something. It is more than 0. So when it is more than 0, we just round it to higher number. In all of these numbers here, which we have, round to 1, right? All these numbers, higher is 1. Do you see? And so we say if the number of students are up to 60. Of course, 60 over 60 is equal to 1. They can be accommodated in bus number 1, right? But what happens if I do 61? Then 61 over 60 is more than 1, of course, but how much more? That let us see. Does it make difference? That's the second point. Does it make difference? It doesn't really make difference. 1.01. It is slightly more than 1. 1.01 to be precise, 6 recurring. But it's more than 1. So what we do is we round it to higher number. And what is higher to this? 2. 1 point something more than 1 plus is 2. Do you understand? 1 plus. That is how we see the ceiling function. So whenever we have ceiling, we say ceiling function means if you divide two numbers and let's say you get 5.03, it will be rounded to 6, not to 5. Ceiling. And in floor function, it gets rounded to 5. We'll talk about it in floor, different video, but similar to this. But you get an idea, floor and ceiling, right? So this function will round to 1 in a floor function. Do you understand? But in ceiling, it will hit 2. That is what it is. It will go upwards, round upwards. And it makes sense for us. As soon as it's more than 1, we need another bus. If it's more than 2, we need the third bus. So more than 2 means 2.001, maybe whatever. It can be rounded to only 3, higher for a ceiling function. So ceiling function is beautiful function which does this job so easily for us. Okay, so remember this ceiling function, and I'm going to use the same example in my video to solve this problem in details, but I hope you've understood what I'm trying to say. Ceiling function, right? So imagine these were our students in set of 60s, right? 60, 120 and 180 and like that, and these are our buses, 1, 2, 3, like that. Do you see that? So we will use ceiling function, and here in our books it is a very standard function used in mathematics, right? And there is a symbol for it. We say symbol for this is kind of like this. This is one ceiling function symbol, and sometimes we make it very simple. And what we do is we write like this, and some people write outside like this, showing that is kind of ceiling, right? At times in some books I've also seen the symbol like this, but closing from top, leaving the bottom away. But all these are ceiling symbols, symbols for ceiling function used in different books, right? So we will use which one you like. We will use this. It looks impressive. Okay, so 2 lines here looks great. So we will use this function as our ceiling function. Okay, so I hope you understand what I'm trying to do here. Okay, for you there's a practice problem. Let me just make sure you understand, right? So I'm writing a ceiling function and I'm saying, well, round them up and tell me how much will they be. So if I write a, let's say a is, that is my ceiling function, right? Outside, and the number here is too small a place, 1.1. What should this be equal to? B. This time I'll give you more room here, and let's say this one, right? And let us say if I have 3.01, then what is this equal to, right? And let's just see. Ceiling function is let's say 5.7. So what should this be equal to, right? And D is, let's say ceiling function is 3/10. Then what should this be equal to, right? So do this exercise, try to understand ceiling function. What is it? Look at the roof. So it rounds upwards. Okay, that's what ceiling function is. And we are soon going to use it in solving problem, the one we just now discussed. Okay, thank you. Enjoy.